Swayam Prabha. Digital India. Educated India.
So, I will introduce myself. My name is Prasad. I'm a professor in the Department of Chemistry, IIT Madras. I joined here in 2006, long back. And I teach physical chemistry. And my area of research is light matter interaction. Right? You shine light on molecules, molecule absorb the light, and then it undergoes various transformations. These transformations can be like physical as well as chemical. Physical transformations means it absorbs the energy and there are some changes happening within the molecule. Molecule will not get destroyed. Chemically, the structure will remain the same. But there will be some energy changes happening to the molecule. That is called photophysical changes. But sometimes when you shine light, chemical reaction happens, right? They are called photochemical reactions. So, when light matter interaction happens, photophysics is there, photochemistry is there. I work on photophysics. So, molecules will not get disturbed or not get destroyed, but it absorbs the energy of the photons, right? Photon carries energy, right? So, that energy will be given to the molecules. Molecule absorb the energy. Now, when we talk about energy of molecules, what I want you to probably, you can have a brief discussion in the group also. That's why I put you in groups. When you say energy of a molecular system or a molecule, what types of energies comes to your mind? Okay. So, I don't want to answer now. You can have a discussion and then each group becomes ready with that answer. Then I will ask one group to present. So, broadly energy means whenever teachers ask energy, energy is equal to, this is a standard equation, right? All energy of any chemical system is kinetic plus potential. But now within the molecular situation, can you further classify energies? So, take a minute, you can have a small discussion. If you want to come close, you can come close. Then I will ask you, take 1 minute. You can talk louder, no restriction on the decibel level, okay? Talk freely and loudly. Okay, so let us hear what you discuss from your group. What thoughts? Oh, is equal to mc square. That's an equation, but that talks about mass conversion to energy, right? The question now is, what are the different types of energies associated with the molecule? Broadly, you can classify as kinetic and potential, but within that, you can further classify. So, let us hear what they discuss. Vibrational. See, that is one particular energy. Let us call it EV. Molecules vibrates, right? So, there will be vibrational energies associated with that. Another one, rotational energy, right? Molecules rotates. So let us let us go by one. Binding energy. Binding energy can be a potential term, right? So let us call it as electronic energy. Okay, so that is binding between, binding means there will be always two things, electrons and the protons. So it's an electronic energy, so let us call it EE. Okay, translational energy, that means there is something the molecular system moves in space that requires energy. Anything else remaining? Electrical energy. Nuclear energy, that is another term. So with these 5 terms, broadly they say that these are the energies associated with the molecular system. Among this nuclear is very special case. We normally don't deal with the nuclear or nuclear reactions, nuclear processes are slightly different class of chemistry. Normally we deal with electronic part. So the electron associated with this thing is basically it carries this much energy terms. Now when light falls on molecules, we know photons carry energy and that energy will be given to the molecules. So when the energy given to the molecule, all these energies get perturbed, right? So this energy will be changing. That part is the study of photophysics, how these energies are getting changed. So depends upon the photon. So you know electromagnetic spectrum, right? Some waves, can you tell? UV, visible, IR. Very nice. So all photons not have the same energy. They have different energy. Right? E is equal to h nu. Nu is the frequency of the light. So depends upon the frequency or the wavelength, energy changes. So when photons of different frequencies fall on matter, different types of energies are given. As a result, different types of energies will get perturbed. Okay, this is the focus of photophysics. Okay. Now what I would do is I have some write-up. I will give each one page to one group. You can take a photo if it is difficult to read. You have a mobile phone, right? Yeah, take a photo, get everybody as a copy. Then there are some questions in this paper. What we'll do is we go question by question. First question, I will tell you when to begin. You just read that text, initial text first. Then I will tell you when to start. Each question will time it so that all teams can go together. Everybody get the paper? Okay. So take a photo and then probably you can. First you read that text which is almost a page. So go through that reading part. I have a few more copies, so probably. You need one copy I need. So you, okay, only one copy, right? But yeah, this is a limited number only. One copy I need. So okay, you can take you took a photo. Huh? Fine. So no need. Okay, okay, take the photos. First you read that paragraph. Questions we can do later. You read the paragraph, ensure that you have some idea about what is written there. Okay. So you are roughly gone through that. Anyway, that page is with you. So let us start with the first question. Okay. You read the question. You'll get about 1 minute or maybe some 30 seconds. You can have a discussion in the team. Find out the answer for question number 1. Go ahead now. So don't find out answer alone. So you can come close. Together you find out the answer. And if somebody is disagreeing, you can have an argument, find out a final answer. So you find out the answer from the text, not from other sources. Okay. Okay, let us see what are the things that is coming to your mind. Okay, let us start from this team. According to you, the question is identify the transitions in the diagram that correspond to fluorescence and phosphorescence and explain the difference. Okay, let us hear. Yeah. You're Steve, right? You're Steve, right? Tell me. Shri. Okay, okay, okay. Fluorescence means S1 to S0. Okay. T1 S0. Okay. One is allowed, one is forbidden. Which is allowed? Fluorescence is allowed. Fluorescence is allowed, phosphorescence is not allowed. Why? Spin multiplicity is changing. So when S0 goes to S1 goes to S0, we call it fluorescence. T1 goes to S0, it's called phosphorescence. What will happen if T2 goes to T1? So with it fluorescence or phosphorescence? T2 to T1. T2 is not shown in the figure. No, that is not in, that is, you can call it. So there are several terminologies coming. So if it is, suppose ground state is T0, can we have a ground state with the T? How many groups say T0 is not possible? T0 not possible? Not possible. What do you? This team? T0 not possible? Okay. Not possible. Not possible. So why you are saying not possible? Because usually there will be 2 electrons in the highest occupied molecular orbital which will be paired. But there are exceptional cases. If you take oxygen, very common element, oxygen molecule, it has two unpaired electrons in the highest occupied molecular orbital. They are not in the same orbital, they are orbitally separated. So, the ground state in the Jablonski diagram of oxygen is a triplet state. So, T0 is possible. Go back and check the MO diagram of oxygen. Okay. The two electrons, only when they are in the same orbital, according to Pauli's exclusion principle, it has to be paired. But if they are in different orbitals, they can have same spin in the ground state also. Okay. So, triplet is possible. So, suppose T0 is ground state and T1, there is a T1. So, T1 to T0, what do you call? All are energy relaxation. It's in that way, fluorescence is an energy relaxation, phosphorescence is energy relaxation. It's all energy relaxation. So, if you define fluorescence and phosphorescence, so that's a question, right? How do we differentiate it? So, one of the technical way you can define this is fluorescence is an electronic transition between the states of same multiplicity, same spin multiplicity. So, that is the way fluorescence is defined, and phosphorescence is electronic transition between different spin multiplicity. Okay, so that part you can note down. That is how you define fluorescence and phosphorescence, which are two important photophysical process. Go to question number 2. Yeah, so that's a relatively easy question. So, we will take answer from this team first. What will be the typical lifetime for the process of fluorescence? 10 to the power of minus 8, 10 to the power of minus 9, in that range fluorescence will occur. Okay, so 10 to the power of minus 9 second is also called nanosecond. If it is meter, it is nanometer. If it is in second, 10 to the power of nanoseconds. So, fluorescence is a process which happens in nanoseconds. Okay. Next question is, which excited state will have a longer lifetime, S1 or T1? And why do you think so? So, let us take from this team. Question number 2, second part. So, T1 is your answer. How do you come to the conclusion? T1? So, intersystem crossing, don't worry about it. The path, so you consider something is in the coming from S1 to S0 and something is already there in T1, it is coming to S0. Only that time we are comparing. The path and all we are not comparing. Okay. So, but something is given in that picture. So based on that you can tell. So faster process is S1. So faster process S1 to S0. Longer lifetime T1 stage. The kinetics and the lifetime, they have an inverse relation. So the rate constant of any process will be 1 over the lifetime of that stage. If the lifetime is high, the rate of the process that dissipate the energy will be less. They are inversely connected. So if the question is which excited state will have a longer lifetime, then the K, which is the rate constant, the longer lifetime will have a slower rate process. So you look at the diagram, they say phosphorescence is a process which is a, okay, lifetime itself is given 10 to the power of minus 3 to 1 second. So it's a very long lifetime compared to fluorescence, which is happening in 10 to the power of minus 8 and minus 9. So T1 is staying there more. So why? That's a question. What do you think? Why T1 is having a longer lifetime? That's also in the question, second question. What could be the reason T1 is having a longer lifetime? Okay, so Dhanlashmi, what do you think? Discussion. Not able to come to a conclusion? Okay, so let us ask this team. It is possible. Possible. So both are possible. S1 to S0, T1 to S0 is both are possible. One is a slow process. One is a relatively faster process. Which one is faster? Fluorescence is a process from S1 to S0. That is faster. What is the time scale? Second is the lifetime. Now T1 to S0, it's a slow process. So lifetime will be high. Lifetime is 10 to the power of. Why it is a slower process? Okay, how about this team? Some thoughts? Okay, keep discussing. Let us see this team. So that is true. Lifetime is low means K will be high. Lifetime is high means K will be slow. That's the relation. The question is, what is the reason? How do you explain that T1 is having a longer lifetime? T1 stays more time than S1. We'll come to it. Okay. I think that answer makes sense, right? S1 to S0, so electron spin. See, the HOMO-LUMO, if you consider, this is the state of S0, where the two electrons are paired in the highest occupied molecular orbital. Now the molecule is excited to S1. So what will be the state in S1? one molecule is or one electron is orbitally separated. It has higher energy. Why it has higher energy? It absorbs the energy of the photon, right? So this electron is jumping to the LUMO, lowest unoccupied orbital. This is HOMO. So this is S0, this is S1. Now from this stage, it has to come to S0. That means this electron has to come back to the HOMO. It can come back because the spins are the same way. Spin is not changed. So it can easily come back. Whereas in triplet, this is the case of fluorescence. Whereas in the case of triplet, what is the situation? This is the situation, right? The spins are parallel. So now if it has to come back, this is called fluorescence. This is called phosphorescence. If this state has to come back to this, the spin flip has to happen. And it's a forbidden process. Forbidden process means what? The process will not happen. Forbidden is not in the literary meaning. Forbidden process also happens. Probability will be less. Okay, so in spectroscopy, somebody says forbidden process, it doesn't mean that process will not happen. Probability of that process will be less. So, because the probability is less, the rate of this process will also be low. That means these states will be staying there longer time. So, that's the reason why T1 stays longer than S1. Question number 3. Answer is there in the text or in the diagram. Carefully you look it. Okay. Rapid. So what is the time? Which is a faster process? So that's why it happened. Okay, that's the answer. What do you think? What is the question? So you can, this light excitation can take into any higher energies. Now, but they are not emitting from there. They come to S1 and then emit. Why? That's the question. Answer is there in that diagram. But how do you explain it? Why it has to take place first before emission? What do you think? Right, but internal conversion, but again, why internal conversion has to take place first? Why can't fluorescence take from S2? That answer is there. Yeah. So internal conversion is a process, but why it has to happen first? Why can't S2 to S0 fluorescence happens first? That's the question. Right, that is fluorescence. Okay. So from S2 to S0, 10 to the power minus 8 second, it can come now. Okay. That's okay. So see, whenever you are exciting a molecule to excite a stage, the way that it comes to the ground state, there are only two ways. One, give the energy in the form of light, or give the energy in the form of heat. So one process is called radiative process, another one is called non-radiative. From S1 to S0 also non-radiative is possible. Okay, so these are the two channels through which it comes back or dissipates energy. But the question here is why S2 to S0 radiative transition is not generally seen. Okay, let us hear from this team. Lifetime of S2 to S1, the relaxation is rapid. That internal conversion, see the time, 10 to the power of minus 12. Fluorescence lifetime, which is higher number? Minus 9 is higher than minus 12. So fluorescence is a faster process. Sorry, fluorescence is a slower process than internal conversion. Internal conversion is a faster process because lifetime is less. So rate is high. So 10 to the power of minus 12 means that process is very fast. So internal conversion happens very fast. So by the time it starts fluorescing, it will be already there in the S1 because the internal conversion is a faster process than fluorescence. That is the answer. Okay. Alright. So question number. So you can excite the molecule to S1, S2, S3. It all depends upon how much energy you are giving. Any energy level you can have. The whole spectroscopy is E2 minus E1 should be equal to HNU. So it can be S1 S0, S2 S0, S3 S0, depends upon what energy you are giving as HNU. So pumping is easy. But coming down, there are various other processes and each process, all these things are happening simultaneously. So faster process will happen first. Make sense? So internal conversion is a faster process. It happens first and then it comes to the S1. Then the other process happens because that rates are relatively low. Okay, go to question number 4. So singlet and triplet, two states are there, no? Singlet means only one type of spin orientation. That's called singlet, one. Triplet means 3 types of spin. That's why it's called triplet. So what are those 3 different types? That's the question. Is the question clear? Clear. Okay. Triplet means there will be 3 different ways of orienting the spins of the electron. Singlet means only one way. And it is calculated based on the 2s plus 1 equation, right? S is the total spin. So if in singlet, what will be the S value? S will be, so there it's paired, right? So there will be 2 electrons, assuming that there are 2 electrons. What will be the total S value? 0, because 1 plus half, 1 minus half. So what will be 2s plus 1? That's why it's called singlet. Okay. Now what will be 2s plus 1 value for triplet state? 2s plus 1. It has to be 3. That's why it's called triplet. So S is what value? 1 value, right? So Then only it becomes 3. So now there are 3 ways you can get 1. What are 2? Okay. So how do you arrange the spins? There are 2 electrons. You can see the triplet is parallel, no? So in this case, it is both up. Both up and both down. That makes sense. So they are all parallel, either this way or this way. Now third one you said, what is that? If you are pairing, then it becomes singlet, no? So that seems to be difficult now. How do we arrange the spin? Any ideas coming? So that question alone, you take it as homework. Tomorrow also we are meeting. Okay, try to find out the answer for that. Move to question number 5. Okay, so let us get the answer from this team. What is the difference between internal conversion and inter-system crossing? Okay, so that is the feature of the rate of the process. How do you define internal conversion and inter-system crossing? Singlet to triplet is inter-system crossing, and singlet to singlet is internal conversion. Okay, how about T1 to S0? Hello, what is that? Is internal conversion or inter-system crossing? Yeah, the name is phosphorescence, but that process can be classified as internal conversion or inter-system crossing is the question. It is inter-system crossing. Singlet and triplet are the two states. Whenever it cross over, you call it inter-system crossing. Okay, if the between the same states, if that movement is there, it's called internal conversion. And internal conversion and this radiative process, the internal conversion is normally non-radiative. It emits heat. It dissipates the energy in the form of heat. But heat is a radiation, right? So then why it is called non-radiative DT? It is a radiation, right? Heat radiation. Huh? You want to say something? Energy? So what we said is, after its excitation, the excess energy has to be given out. Only two channel, one is radiative, another one is non-radiative. In a Jablonski diagram, radiative processes are straight lines, non-radiative are wavy lines. Okay, so this is called internal conversion, this is called inter-system crossing. Now my question is, this non-radiative means they say it gives the energy in the form of heat, but heat is a radiation, that's what I am asking. So why it is called non-radiative? Even the diagram looks simple, there are a lot of things to think about it, right? Okay, so they say non-radiative because it's not an electromagnetic radiation. That is one possible answer. Heat can also be given out not as radiation, right? There are other ways of conduction of heat. What are the different ways of heat conductance? 7th standard you learn, no? Huh? Convection, conduction. So there are different channels through which heat can be dissipated, not in even the form of radiation. And another one is heat radiation, you don't have to consider it as an electromagnetic radiation. That's not coming in that. Yeah, so heat is not a form of photon. So that is another why it's called radiative transition. In this diagram, they define it as only in the form of a photon emission. Okay, great. So internal conversion, inter-system crossing. There is one more terminology which is not there in the diagram. VR, vibrational relaxation. So there is internal conversion. This is called vibrational relaxation. So what is the difference between IC and VR? No, IC is here, no? This is IC. This process is IC. Suppose it coming here as a non-radiative, this also IC. This is also IC. Then what's the difference between IC and VR? Within the state, non-radiatively the energy is dissipated, that is called vibrational relaxation. Because each state, S0, S1, S2, these are all electronic energy levels. Each electronic energy level has several vibrational. In between vibrations, there are several rotational. So the energy required for rotation, so the energy requirement in this process, have you come across that? How much energy is required for these processes? Which is the highest, which is the lowest? That means to vibrate a molecule, how much energy is required? To rotate the molecule, how much energy? What is the scale of energies? Or comparatively, which is lower, which is higher? Okay, so the way it is coming is, translation is the least one, then comes rotation, then come vibration, then come electronic. So these are all electronic energy levels. Okay, So within each electronic level, there are several vibration energy levels. Between the vibrational, you can think of several rotation energy levels. Because the energy gap between two rotation energy level is relatively smaller than that of two vibration energy gap. The energy required for rotation, vibration, electronic are different. Electronic is the highest one. So when you shine, say for example microwave, molecules start rotating. Microwave has a energy relatively low and rotation also needs lower energy. When you shine IR, infrared, molecules start vibrating more after absorbing that energy, because that energy is matching with the vibration energy gap of molecules. Electronically is UV visible. Ultraviolet and visible light, if you shine on the molecule, it absorbs that energy and then excites electronically. S0 to S1, S0 to S2, like that. Okay, alright, so let's go to the last question in that one, 6. Increasing order. You write it after you discuss and then write it, then I will come. In order. Okay. What is order? Internal conversion, then fluorescence, then intersystem crossing, then phosphorescence. Okay. Minus 12, minus 8, minus 4, minus 3. Yeah. Oops. What is that? Okay. What is order? Still discussing? Okay, another 30 seconds. What is order?
Internal conversion, fluorescence, intersystem crossing, phosphorescence.
What is order?
Internal conversion, fluorescence, intersystem crossing,
And phosphorescence.
So what is the confusion?
internal conversion, fluorescence, intersystem crossing, phosphorescence.
Because minus 10 to the minus 12 means that process is fast, because that is the time of the lifetime is given. See that relation, k is equal to 1 by tau. Tau is given, lifetime. Okay, that high means k will be slow. So this tau low means k will be high. So 10 to the minus 12 is very low. That k will be very high. Okay, that's a confusion. Okay, so all of you have given the right answers.
SwayamPrabha. Digital India. Educated India.